Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we're looking at the relationship between time and concentration in chemical reactions. So I have a few problems that we can do today. There are 4 of them, so this video is going to be a little bit on the long side. If there's a particular type of problem that you'd like to see, you're welcome to fast forward to that problem. But I feel like this is a nice survey of the types of problems that you could see in this section. So let's get started. The first question states that the decomposition of hydrogen peroxide is a first-order reaction. And we are to suppose that the rate constant for this reaction at 400 degrees C is 7.6 times 10 to the minus 4 power per seconds, which is the proper unit for a first-order reaction rate constant. Given an initial concentration of 0.52 molar for hydrogen peroxide, what is the concentration after 7.7 minutes? We are also asked how long it will take for the concentration of hydrogen peroxide to reach 0.42 molar, and also how long will it take to decompose the hydrogen peroxide by 85%. So we can break this up into 3 different problems. The first one is asking us for the concentration after 7.7 minutes. So we're going to start by saying, this is part A, let's turn 7.7 minutes to seconds. So there's 60 seconds in a minute. Our minutes cancel out, and we're left with seconds, which is 462 seconds. Next, we want to set up our equation that we would normally do for the time concentration formula for a first-order reaction. Now, the reason why I changed it over to seconds instead of minutes is because our rate constant is given to us in per seconds. And we want our units to match in order to have the proper cancellations occur. You could just as easily change the rate constant to per minutes if you prefer to work in minutes. So let's get started. Typically what you're dealing with is for a first order would be the natural log of some species is equal to the natural log of that species originally minus the rate constant times time. Well, this is our time right here. This over here is our rate constant. And our initial concentration is given right here. So now it just becomes a plug and chug. So this becomes the natural log of 0.52. The reason we don't put molar is because this is always in comparison to a standard, which at normal, the normal standard would be 1 molar. So this is true for both the original concentration and the final concentration. Then we say minus 7.6 times 10 to the minus 4 per seconds times 462 seconds, which gives us approximately negative 1.005. I made a little 5 because it's an insignificant digit and we don't want to keep our insignificant digits, but we do want this in terms of trying to have completeness. Recall that this is talking about the natural log of a concentration. We want the actual concentration. So we're going to say that the concentration of A is equal to E to the negative 1.005 0.005 power, which gives us about 0.366, which gives us our final answer being 0.37 molar. So after 7.7 minutes, our hydrogen peroxide has gone from a 0.52 molar hydrogen peroxide to a 0.37 molar hydrogen peroxide. So now we want to know how much time it would take to get hydrogen peroxide to go from 0.52 to 0.42. So that's our question B. We could set up the same problem, the difference being that instead of putting our T in, we don't know what T is yet, so this is no longer valid for part B. And we're just going to put in our initial concentration, final concentration, and our K. So if we wanted to solve for T, let's just do it algebraically. First, you would subtract natural log from both sides. So we get the natural log of our final concentration minus the natural log of our initial concentration is equal to negative KT. Well, the properties of logarithms tell us that a logarithm minus another logarithm is the logarithm of the two species inside the logarithms, the quotient of them. So we can rewrite this as A over A naught is equal to negative KT. And then dividing by K to both sides, we get T is equal to negative natural log of A over A naught all over K. And that'll give us our answer. And this is actually where the natural log of 2 comes into place for half-life, because if the initial concentration was any number 1, let's say, and the final concentration is 0.5, 0.5 divided by 1 is just 0.5, so you end up with the, and if you want to take this negative and bring it inside, the properties of logarithms state that it becomes an exponent. So 1/2 to the negative 1 power is equal to 2. So there's your natural log of 2. Okay? But that's getting ahead of ourselves. So now we have our time equation, and we're just simply going to plug in the information. So this is T is equal to negative natural log of 0.42 over 0.52 all over our K constant, which is 7.6 times 10 to the minus 4 per seconds, which means our time will be given to us in seconds. So that gives us, let's see, that would be, if you do this out, becomes 281 seconds, which is significantly less than our original 462. Makes sense because it should take less time for it to reach 0.42 molar than it did to reach 0.37 molar. Our last question is asking us how long will it take to decompose by 85%, which means that we need the difference between 100% and 85%, which is 15%, because 100% minus 85% is equal to 15%, or 0.15. Okay? And now we just need to use that same time equation right here that we did previously. And we're just going to plug in 0.15 instead of A over A naught. So negative natural log of 0.15 divided by our K constant, which I'm not going to write out, but it's right here. That gives us 2,496 seconds, which you can then use unit analysis to say, oh, well, divided by 60, that gives us the total number of minutes, and that gives us 41.6 minutes. So that's a nicer number to deal with than the larger 2,496. That's why I converted it, but you don't have to. You generally go with whatever the directions say. So that's how you do these types of problems. The other thing that I probably should mention is you may be wondering, well, if this is negative out here, then why is it that this term became positive? It's because the logarithm of any number less than 1 is going to be negative. So negative times a negative cancels each other out and becomes positive. And that's why that occurs. Okay, so let's go on to the next problem. So we're presented with the problem where in a decomposition of nitrogen, dinitrogen tetroxide, which would be N2O4, at 250 degrees Celsius is studied in an experiment by correlating time with the partial pressure of dinitrogen tetroxide with the following results. And we're given the time that has spanned as well as the partial pressure. And we're asked whether the decomposition of dinitrogen tetroxide is a first order reaction, and if so, what is the rate constant? So here's how we would approach this problem. We'd start with the fact that we're looking at questioning whether it's a first order reaction. Well, if we were to linearize a first order reaction, we'd say natural log of the concentration is equal to negative KT plus the natural log of the initial concentration. So what this actually looks like is a Y is equal to M X plus B. So it's just your normal linear equation. It just looks kind of funky. So in this case, we would create a table where we would just do time in seconds. So we just copy the information that we already have. So 0, 100, 150, 200, 250, 300, and then we would want the natural log of pressure that's given, because this is supposed to be our x term, and this is supposed to be our y term. Okay, so when we're doing that, our y term is a natural log of the concentration, or in this case, the pressure. So we would need to take the natural log of P to get the proper y term. And when you do that, you find you get 5.513 and then 5.3808 and 5.247, 5.153, 5.024, and 4.868. Then you would want to plot the natural log of the pressure as a function of time, and you would get, in this case, some kind of linear function like that. I didn't actually go through, you could do Excel to do this, but honestly, in the courses here, you will probably not have to do that. You would probably just have to do it by hand, and in which case you would just do it simply as I've done it here. So this term right here would be the natural log. So that would be the natural log of pressure original, and then you would have this linearization, which would equal natural log of 248 mmHg. And in order to, so seeing that it's linear in this case, you would probably have to plot these as individual points to validate that they are in fact linear or approximately linear. Or alternatively, you could use a graphing function like Excel or your graphing calculator as it is available to you. But generally speaking, you will find this to be relatively linear. And under those circumstances, you would then look and say, okay, we've got a negative k here. So this slope, so m is equal to negative k. So the rate constant would simply be m. So negative m rather. So negative m is equal to k. Which, if you were to do this out, you could just do rise over run. And you end up with approximately 2.15 times 10 to the minus 3 per seconds. Okay? And that also makes sense in a unit, in terms of units, because time in this case is done in seconds, whereas the natural log of a unit doesn't make any sense, so it does not have a unit. And in fact, when you're, like I said previously, when you're using the natural log of something, you're relating it to its standard, so the standard pressure is what it's related to, and that's why it doesn't show up. Typically, it would be in terms of bars, but in this class, it's millimeters of mercury. Okay. So, our next question presents that the radioactive decay of cobalt-60 is a first-order reaction. The rate constant at 100 degrees Celsius of 4.89 times 10 to the minus 9 per seconds. And they want us to calculate the half-life of the reaction. Now, just as a little disclaimer, I would like for everyone that watches this video to note that all radioactive decay processes are first-order reactions. So none of them depend on the initial concentration. However, they are temperature dependent. So it's important to recognize that even first-order reactions have some measure of dependency on temperature. Okay, so for first-order reactions, we know that the T1/2 is equal to the natural log of 2 over K. Now recall I explained how the natural log of 2 came about. If you didn't catch it, it was 2 problems ago. Briefly mentioned it, but it's an important concept. So otherwise you're just memorizing, which is fine for this class, but if you intend to pursue more chemistry classes in the future, you'll want to understand where that 2 comes from. Okay, so then this becomes the natural log of 2 over 4.89 times 10 to the minus 9 per seconds, which will give us seconds as our final product, which in this case is 1.6195 times 10 to the 8th seconds, which we can then convert to hours, days, weeks, months, years, whatever we'd like. If you were to multiply it by, we can do the conversion right here, 1.6195 times 10 to the 8th seconds, and we want to get rid of seconds. So for every 3,600 seconds, you have 1 hour. And for every 24 hours, you have a day. And approximately for every 365 days, they'll have a year. So our seconds will cancel out, so will our hours, so will our days, and we'll be left with years, which in this case is 5.14 years. So it has a pretty long half-life, though not nearly as long as some things. Last question, last problem, presents the decomposition of nitrogen dioxide is a second order reaction. Now we have been talking about only first orders, but recall that there are other orders, including zeroth and second order. And if you pursue more chemistry, you'll find that there are even more out there. There's even orders that are not whole numbers. So it's important to understand that, but for this class, zeroth, first, and second are the only ones truly addressed. So it says that the rate constant is given as 6.0 times 10 to the 9th per meters, edit. So it's given that the rate constant is given as 6.0 times 10 to the 9th per molars per second at 32 degrees C, which is consistent with the units that you would expect for a rate constant in the second order reaction. If the initial concentration of nitrogen dioxide is 0.068 molar, calculate the concentration after 3 minutes. Also, calculate the half-life for both when the initial concentration is 0.62 molar and 0.4 molar. Now, it's important to recognize that the half-life for a first-order reaction is not dependent on the initial concentration, but for a zeroth or a second-order reaction, it is dependent on the initial concentration. So let's start with the first part. Let's call this A. So we're given our K constant right there, and we're given our initial concentration right here, and we're given a time. But I want to have consistency in my units, so I'm going to convert time to seconds. So 3.0 minutes, 1 minute, 60 seconds, minutes cancel, and I'm left with 180 seconds. Okay? Now we're going to set up the time concentration formula for a second order reaction, which is 1 over the concentration of the species is equal to 1 over the initial concentration of the species plus KT. Okay? So if we were to go ahead and plug in our values, we can do that easily enough here. So 1 over 0.068 molar plus 6.0 times 10 to the 9th power per molar per second times 180 seconds. Now I can tell you right now that this term right here, this constant, is going to dominate everything else. So it's important to recognize that no matter what, this is going to be a very fast reaction. And in the future videos, you'll find that this K value, how big it is or how small it is, will help determine the direction of the reaction. This being as large as it is, really helps to push the reaction forward in a very, very, very quick fashion. Okay, so plugging all that in, we get 1.08 times 10 to the 12th per molar. Okay. However, this is relating to 1 over our concentration, and we want our actual concentration. So final concentration is equal to, and this A, where A is equal to N O2, for clarity's sake, is equal to 9.26 times 10 to the minus 13 molar. So in the course of 180 seconds, 3 minutes, we went from a relatively modest molarity down to practically nothing. This would be nearly undetectable under most circumstances. So the reaction is pretty much used up. So thinking about that, let's look at the half-life of this thing. Meaning, how long would it take for us to consume half of the original content? So T1 half for a second order reaction is equal to 1 over K times the initial concentration. Again, initial concentration is important to include in the half-life for a second order reaction or a 0th order reaction. Okay, so if we were to do this out, we could, for the first term, we could say 1 over 0.62 molar times 6.0 times 10 to the 9th per molar per second, which will give us the proper units as molar and per molar will cancel, and we'll be left with per seconds in the denominator, which will give us a final result of seconds. And in this case, it is a measly 2.69 times 10 to the minus 10 seconds, which is 0.269 nanoseconds. It's very, very fast. For the other concentration, we simply plug in 0.04 instead of 0.062. So 0.040 molar, 6.0 times 10 to the 9th molars per second. And that gives us, looks like 4.17 times 10 to the minus 10 seconds, which would just be 0.417 nanoseconds. So again, very, very short amount of time. I hope this video was helpful to you in understanding the relationship between the time the reaction undergoes as well as the concentration of the species in the reaction.